In this course, we discuss space of functions. Like we saw that given a measure space, then the integrable functions form a space that has a lot of structure, as a topological space with a norm that is complete. Now we'll do something analog. Instead of varying functions for a fixed measure, we'll really consider all possible measures on a given space with a fixed sigma algebra. So let's try something. So what we want to do, we want to consider vector spaces formed by measures. Now, the first problem is that, okay, summing measures gives a measure, but when you multiply by a scalar, a measure, if the scalar is negative, then it's not a measure in the sense we define. We only consider measures that are positive valued. So we have to relax this definition of measure and allow also functions, measures that have not only positive values, but any real value. So to do this, we need to allow for real valued measures. They're also called sign measure. So actually, one can also be even more general and not only give measures that are valued into R, but also valued into Rn. So let's define real and vector measures. So we fix a set and a sigma algebra, so a measurable set, or measurable space, and we can also fix an integer. We said an RD valued measure on EE is a function mu from the sigma algebra E valued into RD, such that, as usual, the measure of the empty space of the empty set is 0, and whenever we consider sequence A1, A2 of sets in E, they are pairwise disjoint. We have, first of all, we have that the series of their measure is absolutely converging. This is a condition that we want whenever we have disjoint countable sets. And the second property is that the measure of this disjoint union is equal to the sum of mu an, right? So we are assuming that this series is converging, is even absolutely converging, and the sum gives exactly the measure of the union of the sets. Okay, so this is the definition of a RD valued measure. Now, if D is equal to 1, then so R valued measure is also called real measure. Instead, if D is greater than 1, RD valued measures are called vector measures. Just by definition, okay? Okay, Now so this is, we want to consider space of RD valid measures. So it's defined M, or better should be M, E, E, RD. This is the space. So the space of RD valid measures. Now this space is going to be a Banach space. Let me introduce the future norm. This is called total variation. So now there is going to be a little bit of ambiguity for the total, what's the total variation, because I'm going to define both a positive measure and a number, and both of them are called total variations in the literature. So maybe I will call one the total variation measure and one the total variation mass, just to not confuse them. Okay, so the total variation measure of RD valid measure mu is the function defined as, we'll denote it like absolute value of mu, or that is applied to A, is the supremum of the sum over n mu an, such that the set A1, A2, and so on belong to E. They're pairwise disjoint, and A is the disjoint union of this an. So we decompose A as sets. In each of them, we take the measure with the absolute value, or with the norm. This is the norm in Rn, and then we take the supremum. This is the definition. Okay, so this is norm or in RT. Okay, and now instead the total variation, let's call it total variation mass to not confuse it with the measure, or just sometimes called just total variation of mu, is, so we denote it as a norm of mu, and is the total variation of the whole space E. Good, so this is a definition. Now here some properties. So facts. So first of all, this absolute value measure is a positive, okay, in the sense of the initial definition of measure, positive finite measure. So it's a measure with the initial definition, and the measure of the whole space is finite, and therefore the total variation mass is finite. And the second property is that M, the space of all measures on E, or like me E R T, with the total variation norm, is a Banach space. So it's a complete, so I'm saying that this thing is a norm that makes this vector space. So this is a vector space, and these norms make this vector space a complete space. Okay, so now another thing that notice that a positive measure, positive measure mu on E. So the measure in the, as we defined at the beginning of the course, with value into 0 infinity, this measure is in M if and only if the measure of the whole space is finite. So this set here contains the maybe in M, now M, I mean M E E R. So the measures valued into R plus into 0 infinity are in this space here only if the mesh only if they are finite value, and really also this and the whole space therefore has finite value. Good. Let's prove that the total variation measure of a vector measure is a measure. So proposition. So let's do the real case. Let's mu be a real measure. So it's a measure with sign. Then we want to prove that the total variation measure is a measure, namely it's a positive measure. It is actually a finite measure. So with the measure, namely what we call the total variation mass, this is finite. It's also easy to see that this is at least the measure of the whole space. So we know that this is finite. This number is finite, but by assumption. But we need to prove that this is, generally speaking, is still finite. Let's remember the definition. So the total variation of so this was the, oh sorry, this is for the set E. So this is the total set E. Okay, but actually this is for all sets. So the total variation of a set E, this is by definition, is the sup of all the quantities written as sum of absolute values of elements A1, A2 in the sigma algebra disjoint such that A is this disjoint union of these AIs. Okay, so let's prove the proposition. Okay, so proof. So what we want to prove. So we want to prove. Oh, first we want to prove that when you take disjoint elements an, then this is equal to the sum of the measure of each of them. Okay, let's prove this inequality as two inequalities. So regarding the greater or equal, so let's fix epsilon, and then for any n, we can write an, so an as a disjoint union over I of elements a and I with, so what I want to say is that if you want to calculate the total mass of, or the total variation of AI or an, this is, we take a sequence that almost realize the sup by an error that is less than epsilon over 2 to the n. Okay, so this is by definition of the total variation. And now what do? We observe that if we now take the disjoint union of an, so these are disjoint. Now if we, to calculate this disjoint union, what we can take is the disjoint union over I and n of this set n, a and I. And therefore, what we have is that the total measure, the total variation of the disjoint union of AI of the an is at least the sum over n and I of the absolute values of ani, the measure of the ni, and by this inequality here, now let's bound, so we putting on the other side, so this is greater or equal than the sum over n of mu of an plus minus the sum of epsilon 2 to the n, right? So now this is epsilon. So what we got, this is true for every epsilon, so tend epsilon to 0, and what we get is, we prove this inequality. Okay, so since epsilon is arbitrary, what we get is this inequality is okay. Let's go to the other inequality. So regarding this other inequality, for all partitions, so we have the disjoint union of un, and we write it as a disjoint union of elements bi. And then what we do, we let a and I to be bi intersect an. So what we have is that bi is the disjoint union of the a and I, and an is the disjoint union over I of the a and I, and therefore the sum of the n and I sum over I, this gives a lower bound for the measure of the total variation measure of an, and therefore now we sum over I of what do we do? Okay, let's use the fact that the measure mu is additive. The measure mu is sigma additive. So if I take mu of bi, this is equal, I'm using this property here, it's equal to the sum over n of the measure of the a and I. Okay, now this is true, so I can take absolute values and I can sum over I. Okay, and therefore now I'm going to bound this term. So this is sum of the sum of over n and I of the absolute values of mu a and I. And now I use this property here, and I get that this is less or equal than the sum over n of mu of an. And now, since this decomposition bi was arbitrary, we pass to the limit and we get that the sup is less than this quantity, and the sup is exactly the total variation measure of this set. So what we get is this inequality here is okay. Good. So we proved that the total variation measure is countably additive on these joint sets. Good. Therefore, this is a positive. This was the condition that was left to prove that this was a positive measure. Now let's prove that this is finite. So the next claim is that this is finite. So it's a finite measure. So the measure of the whole space is finite. This is what we mean. Okay, so if not, the measure of the whole space is equal to infinite. So there exists sequence an of measurable sets disjoint such that the sum of the absolute values of these measures is as big as we want, and in particular we can make it bigger than the measure of the set. Let's remember that this is finite, it's a finite number, so the absolute value is finite plus 1 times 2. So this is a finite number. So in particular, if this is infinite, we can find some decomposition of the space, or just some disjoint sets whose sum of their measures, sum of the absolute values of the measures is as big as this number. Okay. Now let's consider these sets. Some of them are positive. These measures sometimes are positive, sometimes are negative. So let's split into two subsequences. So we split the sequence an into two sequences according whether mu an is negative or non-negative. Okay. And so so what we have is where that half of them should sum up at least to this number here. So there exists subsequence nk disjoint such that, let's call their union, disjoint union f. What we have is that the measure of f is equal, or the norm, it's equal to the sum of the measure of the an nk, and this is just because if they are all positive, then it should be clear, because that this is just the additivity of mu, right? If they're all negative, then this is the additivity of minus mu. Right? Okay, so the additivity So this comes from the fact that mu is additive. And this is, as we said, this is at least, since it is at least half of the sum, then we can bound this with mu of E plus 1. Okay, very good. Okay, so this set has this bound on the measure. But now, on the one hand, so in particular, mu f is measure greater than 1, and the measure of the complementary set, again using additivity, this is equal to the measure of E minus the measure of F, and this is greater or equal to the measure of E minus the measure of F. And as we said, since this is at least the measure of E plus 1, what we get is that this is also greater than 1. So what we understood, we have two sets whose absolute value of their measure is greater than 1. Okay, so we split the set in the space into sets of measure at least 1. On the other hand, since we have that, so we know that the total variation is a measure, so the total variation of F plus the total variation of the complement, it's equal to the total variation of E, which we are assuming is equal to plus infinity, which means that one of these two numbers should be equal to plus infinity, at least. Then either mu of f is equal to infinity, or mu of E minus f is equal to infinity. And now we continue we choose one of these, right? That still measure 1 in any case. So what we do, so one can iterate and construct a sequence Bn of elements in the sigma algebra disjoint, such that each of them has measure greater than 1, just iterating. And now this gives a contradiction. We get a contradiction with the definition of real measure. Since they are finite valued, what I mean, so again, split this sequence in those for which you really have a positive number and for which you have a negative number. Okay, so let's say that you have infinitely many with positive value, and now what you have is that the union of these sets is, since they are disjoint, you can bind it from below by 1 times how many times you have how many sets you have, but you have infinitely many. So it means that you find a set that has mu measure equal to infinity, but this was not. So I'm using the additivity again. But we assume that our real valued measures are finite valued. So we get a contradiction, and this proves that the total variation is finite valued. The total variation measure is finite valued.